You can see the screen.
Yes, sir.
Okay. Any questions from last week? Any concepts which are not clear?
No, sir.
Okay. Right. So I'll continue. So you know what's an equipotential surface, right?
Yes, sir.
The point on all the points on that surface will be the same potential. Okay. So here there are two equipotential surfaces. One is at potential V, another one is V plus delta V. So they are very close surfaces. Okay, so we have to relate the electric field to the potential gradient, or we have to relate the electric field and the potential. So how they are related is electric field and potential gradient are related, and the relation is the negative gradient. Okay, so we just have to use this thing in problems, but just to get an idea, to move from one point to another point, the work done will be the work is done on the system, it will increase the potential energy. So the increase in potential energy, here I'm taking decrease. So it will be work is E dot dl, work done on moving a positive charge from A to B. Okay, so this work is done by the electric field. So work done on the system is minus E dot dl. So the electric field is related to the potential as a negative gradient. This also I started last time. So when will the potential energy of a system increase? If you consider a system, when will the potential energy of the system increase?
When the distance is very small.
No, the basic thing is when work is done on the system, okay, its energy will increase, right?
Yes, sir.
Okay, so here it's potential energy. Okay, so when work is done by the system, it will lose energy, and that is potential energy. So initially, nothing is there. So I'm building a system of two charges Q1 and Q2. So first I bring the charge Q1 from infinity to this point. For that, no work is done because there is nothing to oppose it. While bringing the second charge, if you assume they both are like charges, then I have to overcome a repulsive force to bring Q2 from infinity to this point. So since I'm doing work on the system, its potential energy will increase. And the potential energy is K into Q1, Q2 by the distance, final distance. Okay, the work is done on the system to create this system. So its potential energy will increase. So when a system has got potential energy, so there is a way to get work out of it, right? Because it has got some potential. If the system has got potential energy, it means that it has got some energy, right? So we can use that energy. So here in this system, after building the system, how can I get the work out of this system? Can you think of a way? If I to hold this Q2 at this point, or if I make this Q2 free, it will start flying away, right? Because of repulsive force.
Yes, sir.
So it will gain kinetic energy.
Yes, sir.
Okay, so that kinetic energy is coming from the stored potential energy.
Potential.
Okay, you have to understand the physics, otherwise you'll make mistakes in the exam. So similarly, if you have a three charges to build this system, first charge will be work done. Second charge have to work done corresponding to this one. Okay, to bring a third charge, I have to do work done in overcoming the repulsive force of both Q1 and Q2. Okay, we just have to remember this formula.
Yes, sir.
Okay. So each pair will give each contribution to the potential energy.
Yes, sir.
Okay. Now suppose if you have an external field, here there is no external field. Here there is a system of charges. Other than this system of charges, there is nothing else that is present. Okay, but suppose if you have an external field, field means here electric field. Okay, to bring the first charge Q from infinity, I have to do some work. Okay, because there will be some repulsive force. Okay,
Yes,
so
sir.
that work required to bring the charge to a particular location R into the value of the potential at that point into the charge Q. Because the definition of the potential at a point is work done in bringing unit positive charge from infinity to that point. That is the definition of potential. So to work unit positive charge, the work done is V. So to bring Q charge, the work done will be Q into VR.
Yes,
Is
sir.
it clear?
Yes, sir.
Okay. So now if I have two charges, I'm building a system of two charges. To bring the first charge, it is same as this one. So it's Q1 into V at R1. And to bring the second charge, I have to find the potential and bring the second charge to the location R2. So I have to find the potential at location R2. I written total because one is because of the external field, another potential condition will give the charge Q1. Okay, so this B total is P at R1, R2 because of the external field plus the contribution at R2 because of Q1. Okay, so this is only to the external electric field, not the total. Okay, so this potential B is due to only the external electric field plus the contribution of charge Q1. Due to charge Q1, there will be a potential at a point R2. That value is K into Q divided by the distance, that is R12. Is this clear?
No, sir. I don't get it.
See, there are two things. One, there is external electric field, and then there is charge Q1. So to bring the
Okay.
single charge first from infinity to this one, in this case, to bring the first charge, the work done is 0. Because
Yes, sir.
there's nothing to opposite. But here there is an external field. Okay, so to bring the first charge, we have to do some work, and that work is using the concept of potential. The potential at location R, where I'm bringing the charge Q, is VR. So VR is work done to bring a unit positive charge. So the work done with charge Q is Q into VR. Okay, now to bring two charges, the first charge, the work done is Q into V at R1. That is by this one. Okay, and the
Yes, sir.
second charge, I have to bring it to location R2. So whatever is the potential at R2, I have to take that into account. Potential at R2 is because of two factors. One is because of the external field. Okay, and then the contribution of the potential due to the charge Q1. So due to external field, the potential at R2 is V at R2. And due to the charge Q1, the potential at R2 is Q1 into the distance between 1 and 2.
Okay.
So the total potential at R2 is due to the external field plus due to Q1. So the sum will be Q1 V1 plus Q2 V2 plus the interaction between 1 and 2. In the previous case where there is no external field, these two terms won't be there.
Yes, sir. Yes, sir.
There's some background noise.
Freedom, mute la board.
Okay, so this is for two charges. So similarly, you can extend to other charges also. So basically here we are using a powerful concept. The work done in moving a charge from infinity to that point is value of the potential at that point into the charge. Okay, but for the second charge, I have to take the total potential. Similarly, for the third charge, I will take the total potential that will be due to the external plus due to charge Q1 and Q2. Okay,
Yes, sir.
so now we move to the concept of conductors. So you know what's a conductor? You know, this is a basic idea, right? You might have learned earlier. So what is a conductor?
Yes, sir. It will pass current only.
Okay, conductor means there has to be free charges to move, and it will move with no resistance. So it's free. So once it is free to move, the inside electric field will be 0. Because if there is some electric field, okay, and there are a lot of free electrons here, right? So the electron will move, and the electron will move in this way here, and it will occupy here. So here will be negative charge, and here will be positive charge. And because of this induced charge, there will be an electric field in this one, which will cancel this one, external field. If it is not cancelling, means further movement of electrons will be there. So more negative charge will be here, and more positive charge will be here. So this movement will keep going on until this net value is 0. So this E is the net electric field inside a conductor. It will be 0. If it is not 0, then the electrons will start moving, until it becomes zero. Is that clear?
Yes, sir. Sir, electric field inside the cell is always zero only.
No, electrostatic means, see, before there will be a transient situation before it becomes static. Electrostatic means it is static, but after a steady state. But we have, sorry. Okay, suppose this is function of time, there will be a transient state, after that it will become steady. So electrostatic means we are studying this part, but we should also consider what is happening before coming to that steady state.
Okay.
This is time. Okay. Right. Now here there is a external here if the okay. Okay. Here if there is external electric field, it will induce charges like this. So here the external electric field direction will be like this. So the electrons will move the opposite direction, and this thing will produce an internal electric field in this direction. So the net of these two will be zero inside. If it is not zero, the electron movement will happen until it balances the outside electric field. So that the net electric field inside should be zero. So conductor, the best way to understand is there are a lot of electrons inside which are free to move. If you don't apply electric field, it will be there only. But if you try to introduce electric field, it will immediately start moving to produce an opposite electric field until the electric field inside becomes zero. If it does not become zero, then the movement will still continue until it becomes zero. Okay, and since inside there is no electric field, to move from one point to another point, the work done is zero. After it reaches the condition where the electric field is zero. So if there is no work done moving from one point to another point, both the points have the same potential. Is that clear?
Yes, sir.
That is the meaning of potential, right? Work done. If it is zero, then the potential, then there is no change in potential. So since there is no electric field inside, the work done moved from this point to this point is zero. So this point and this point should be at the same potential. And here there is a conductor like this in which there is a cavity. So the electric field here is zero. Otherwise, the electrons will move until it becomes zero. And here inside there won't be any charges on the inner surface. So the electric field inside the cavity will be zero.
Yes, sir.
And okay, I can make this complicated if you want. But so suppose I place a positive charge here. Okay, then in that case the situation will change. In that case, the negative charge will get induced in this here. Okay, so the electric field lines will start from here, go and end here. Okay, but still here it will be zero, the electric field. If it is not zero, then the electrons will start moving here to stop this electric field from entering this one. Okay, but inside, if there is no charge, then the electric field inside and the surface charge on the inner cavity surface will be zero. And this principle is used for electrostatic shielding. So suppose I want to use a galvanometer, and galvanometer reading will get affected because of electric field, right? Okay, suppose I don't want to make that error, I'll put this galvanometer in a metal box. So this is like inside a metal cavity. So here the inside the electric field is zero. So that way the galvanometer reading will not be affected by external disturbance. Okay.
Yes.
So conductor means there are free electrons to move so that the electric field inside is zero. So next is dielectrics. So dielectric means the thing is not free, but it will get polarized. Okay. Suppose an atom is there. In general, the center of the positive charge is the center, the nucleus, and the center of the electron cloud, which is also at the center, they will be at the same location. Okay, for a neutral this thing. But once you apply an electric field, there will be a small separation. The positive will move here, and the negative will move here. So it will become a sort of a dipole. If you look at the dipole as a whole, then it is neutral. But since there is small separation of the charges, there will be electric field from positive to negative. Okay, so on the surface, some positive charge will come here, some negative charge will come here. this picture is simpler to understand in case of parallel plate capacitor. Okay, so all the individual molecules will get polarized like this. So if you take any volume inside like this, okay, the charge is neutral, right?
Okay.
But on the surface, if I take a volume like this, then there's a net positive charge. So similarly, if I take a volume like this, okay, then there is a net negative charge. So I can take these two volumes like this, and the remaining has one volume. So inside this inner volume, the net charge is zero. Okay, so on the surface, there are some surface charges. So it's as if it's producing an electric field. So this polarization charges will produce an electric field in this direction, so from plus to minus, and the external electric field is E. Okay, so the net electric field will be E minus this effect. In the case of conductor, this induced will be equal to that external, so that the net electric field inside is zero. Because inside a conductor, we have a lot of free electrons. Here, there are not free electrons, but whatever is there inside, it will get polarized. Okay, so because of that, it will partially cancel this external electric field, not fully. Conductor will cancel it fully, but dielectric will cancel it partially. Okay, and this, you know, for a dipole, the polarization is from negative to positive, right? The direction.
Yes, sir.
If you remember, so capital P is the total. This is for a single dipole. So for this entire volume, I just have to add all the p's because all the p's are parallel.
Yes,
So
sir.
capital P is the total dipole moment of this dielectric, and that will be proportional to the electric field. If the electric field is more, means this separation will be more because it has got more force. So the distance between the dipoles will increase. So that is 2a, right? Or we can also say d. So 2a increases means what will happen to p, the dipole moment?
Increasing.
Yeah, because p is q into 2a. Once q is fixed because it's the charge, only 2a can increase by increasing the electric field. So as electric field increases, the capital P will increase. That's what this relationship means. And there is a proportionality constant, that is epsilon naught into chi e. And chi is depending on the dielectric property. So it's a property of a dielectric medium. So if this chi e is more, means then the amount by which this electric field is reduced will be more. Okay, so next is capacitors. So here we have two conductors, conductor 1 and conductor. Whenever I say conductors, you should know that inside there are a lot of free electrons because we are considering solid conductors. Once there are a lot of free electrons, the inside electric field will be zero under steady state. Transient there will be something happening, but in steady state, the inside electric field will be zero. And this sort of configuration is possible because electric field from here will end here, but it will not enter this conductor. Inside will not enter. So this sort of pair of positive and negative charges will form a capacitor. And the value of the capacitance is given by Q by V. So to understand this thing, and because of this separation of the charges, there will be electric field like this, right? Electric field is always from positive charge and negative charge. Okay, and the potential difference between these two is VE dot dl. That is the definition of potential, right? It's actually dV. Yeah, minus E dot dl. Okay, that is dV. So to get the total, we have to integrate this one. Okay, so if electric field is stronger, electric field will be stronger if the amount of Q is more, right?
Yes.
If 1 coulomb is giving some value of electric field, 2 coulombs will give twice that value. So whenever Q increases, the potential increase. So here the Q increases means V will increase. Okay, so if you draw this plot of Q versus V, so how will the plot look?
Straight line.
Yeah, so it's linearly proportional. This is for a simple or you can say ideal capacitor. And this slope is how much?
Q by V.
Q by V. And what is that Q by V? That constant of proportionality is defined as the capacitance.
Yes, sir.
Okay, this is similar to the Ohm's law for resistance. Okay, so there voltage, if you increase the voltage, the current will increase, and the constant of proportionality is the resistance R. Right here also, if you increase the voltage, the amount of charge will increase, or also other way also, if you increase the charge, the voltage will increase, and that constant of proportionality is the capacitance C.
Yes, sir.
And parallel plate capacitance, this is a here this is a conductor of arbitrary shape, but to solve problems you need neat shape conductors. So this is a sort of a simple capacitor where there are two parallel metallic plates. So there will be charge on the surface. Okay, and this distance between the two plates is very small. So for all the points inside, not here, for the points which are a little bit inside, it's as if that the plates are infinite. This concept you know, right?
Yes, sir.
Okay, so once you say infinite plates, then what is the value of electric field coming out of this infinite plate?
Q by epsilon.
In terms of sigma, it is sigma by 2 epsilon naught, right?
Yes, sir.
And there is one more electric field because of this negative plate, and the direction will be here, and there is the same electric field here. So it will be sigma by epsilon naught into 2. Okay, so inside the capacitor plates, the electric field here is sigma by epsilon naught. And in terms of voltage, the voltage and electric field are related like this, because V is integral E dot dl, and E is uniform, right?
Yes, sir.
Because D is very, very small. So in that case, E will come out. So integral dl is just D. So it's a uniform gradient. And electric field is okay, sigma by epsilon naught, and sigma is Q by E.
Yes, sir.
With sigma by epsilon naught into D, and capacitance is the ratio of Q by V. So from this we get the derivation of this capacitor of a parallel plate capacitor epsilon A by D. All the green ones are formulas which you have to remember. This is for a parallel plate capacitor. Okay.
Yes, sir.
And okay, this is a simple conceptual question. In Q versus V plot of two lines are of different slopes, which one corresponds to higher capacitance?
More slope means more.
So more
It's very
slope.
steeper.
So two lines are there. So whichever has got the most of this one, that will have a higher capacitance, because capacitance is Q by V. It's also same as delta Q by delta V, or dQ by dV. For a straight line, delta Q by delta V is same as dQ by dV, and also same as Q by V. Right, if it is passing through origin. So higher slope means higher capacitance. Same is true for resistance also, for using Ohm's law. Okay, but instead of plotting the Q and V like this, if V is here, then Q is here, then what is the slope corresponds to?
1 by C.
Yeah. Okay, effect of dielectric on capacitance. So capacitance is Q by V, right? So what will have happened to the value of capacitance because of the dielectric introduction? Will it increase or decrease? Capacitance is Q by V, right?
By D.
Okay, so suppose I put the dielectric. So then to create the same, okay, if the amount of charge which I have to put with the dielectric to create the same potential difference, QD will be greater than Q. Is that clear? Because some amount of electric field is cancelled because of the dielectric. This is a positive plate, this is a negative plate. Okay, so suppose when the dielectric is present, the electric field which is inside is less, right?
Yes, sir.
Because there will be some cancellation because of the dielectric polarization. Okay, so to have the same potential means I have to create the same amount of electric field. So to create the same amount of electric field when the dielectric is present, the charge here should be more.
Okay.
Yes.
Okay.
So that's why the charge which is required when the dielectric is present to create the same potential difference V should be more when the dielectric is not present. So that means that capacitor of when the dielectric is present is more than the capacitor without the dielectric. Okay, and this turns out to be this capacitor with the dielectric is K times capacitor without dielectric. And this K is the dielectric constant and it is greater than 1. And if it is greater than 1, then the capacitance will increase. Is that clear? And also you can see the permittivity of the dielectric medium is increased by K epsilon naught, because capacitance of a parallel plate capacitor is given as epsilon A by D, right? Epsilon is generally used for. If it is A it means epsilon naught. If it is the dielectric means you have to put K epsilon naught. Okay, and this K is greater than 1. The capacitance with dielectric has increased by a factor K. Okay, so we can combine capacitors. So here there are two capacitors, C1 and C2. So if you have to replace this by a single capacitor, so what will be the value of that capacitor? I have put an equivalent capacitor. So what will be the value of this equivalent capacitance in terms of C1 and C2? You know this formula, how to relate C equivalent to C1 and C2?
Yeah,
You know series combination of resistance, right?
yes, sir.
So similarly, series combination of capacitor. So how will the capacitance combine? In terms of resistance, how will it combine? R1 plus R2, right?
Yes, sir.
If you have two resistances, the effective or the equivalent resistance is R1 plus R2. So here I have two capacitors. So what is the equivalent capacitance?
C1 plus C2.
It's actually
1 by C1 plus 1 by C2.
it is opposite to what is happening in resistance. So 1 by C1 and 1 by C2 will combine to give 1 by C equivalent. Okay, so the how do you understand that one? So you have to see what is adding here. The voltage is lag, right? Voltage equivalent will be V1 plus V2 because voltage equivalent is across these two terminals. See A and B, it is the same A and B here also. Right? So and the drop here is V1, say, and the drop across this plate is V2. So V equivalent equal to V1 plus V2, right? And V1 is and the charges will be same. If there is plus Q here, minus Q here, and here will be plus Q. And why are these two charges same and opposite sign? Magnitude is same, but the sign is opposite. Why is that so?
Sir.
See here there is plus charge, plus Q. No, this plate is plus Q, and this plate is minus Q. Okay, and this plate is plus Q, right? And this plate is minus Q. So why are these two plates having equal magnitude charges with opposite sign? Why can't this be, say, some Q2 and minus Q2, where Q2 is different from Q, but this magnitude of Q2 is same as Q? Why is that so? You know why?
No, sir.
Okay, because see, this is a metallic plate, and this is also a metallic plate, and this is connected by wire, right? Okay,
Yes,
so initially, when there is no charge, after that battery will be connected outside here, and the charge will get induced. But initially, when the thing was not charged, the total charge of this combination is 0, right?
Yes, sir.
Okay, because 0, 0, everything is 0. So, and this is all insulated. With dielectric, there can't be any charge which is flowing across this. But once I connect this external battery, then there'll be induction of charges will get induced. And but if I take this thing as a system, initially there was 0 charge. So finally also there should be 0 charge because these are all insulators. The current cannot flow along this dielectric. Okay, so the net charge of this body should be 0. So if there is minus Q here, there should be plus Q here, so that the net charge is same as what was there previously. Okay. So similarly, initially these two will also form a system. This metallic plate and a connecting wire, battery, this connecting wire, and this plate along with this battery. This will form a closed system, okay, in which there was no charge because before the battery is being connected, I just connected by a plain switch. So in that case, there was no charge. So once I connect this battery, charges are induced, but the initial net charge inside this full system or body is 0. So finally also should be 0. So whatever plus is here, the corresponding minus should be here, so that the net charge inside this is 0.
Okay.
Okay, by conservation of charge. So in general, when you have series connections like this, the charges across all the capacitors will be same. V plus Q minus Q plus Q minus minus. Okay. So V1, how can you write V1? V1 you can write as since charge is same, you could see V, right? So C1 V1. So V1 I can write as Q by C1. And similarly V2 as Q by C2, and V equivalent is Q divided by C equivalent. I'm saying the same plus Q will be here and minus Q will be here. Okay, so from this we'll get this relation 1 by C equivalent equal 1 by C1 plus C, 1 by C2. Is it clear?
Yes, sir.
So in series combination, you have to remember the voltages will add. Okay, so similarly, okay, this is more than, I'll come back to this. When here the capacitors are connected in parallel. How do you know they are connected in parallel?
Positive plate to another positive.
Because the potential difference between these two things is same as potential difference between these two. Both are the same potential V. But here, the potential difference between these two and the potential difference between these two need not be same. Okay. Whatever is the total potential of this battery will get divided between these two, but it need not be equal.
Yes, sir.
Okay. But here, the battery is here, and the terminals of the battery are connected to the individual capacitors. So the potential difference across all the things will be same. So this is called parallel combination, and here C equivalent is how is it related to C1 and C2? If we replace this with single capacitor is plus. Okay, so it's opposite to the resistance combination. So here, how do you get this relation? You have to see what will add. With C equivalent will have a charge Q and then minus Q here, and this Q will be Q1 plus Q2. So here what will add are the charges Q equal to Q1 plus Q2 and Q is C into V, right? So C equivalent into V equal to C1 V plus C2 V. So from this you get C equal to C1 plus C2. So in the case of parallel combination, the individual charges will add to give the total charge. And in the case of series combination, the voltages will add to give the total voltage. Okay.
Yes, sir.
Right. So if you have more than one capacitor connected in series, what will be C equivalent here?
1 by C1 plus 1 by C2 plus 1 by C2.
1 by C equivalent will be equal to sigma of 1 by Ci, where I is from 1 to n. Is it clear?
Yes.
Okay, similarly here in the parallel combination, C equivalent will be summation of Cl. Okay, and another way to understand this thing is, see, for a parallel plate capacitor, C is epsilon naught A by D, right? I'm assuming the dielectric is here. If dielectric is here, we have to put K. Okay. Here, in the case of series combination, you can think this as this is of dielectric thickness D1, right? And this is D2, so on like that. This is D3, and this is Dn. So the effect of this thing will have so D of equivalent. So here D's will add. D of the equivalent capacitance will be equal to D1 plus D2, so on up to Dn. And D equivalent is 1 by C equivalent. And K is same for all capacitors, epsilon is also same. And assume all the capacitors are same area. Okay, so this will give 1 by C1 plus 1 by C2 plus so on to 1 by Cm. This factor will cancel. K epsilon naught A, which is same for all the capacitors, will cancel. Is that clear? Okay. So we can think as if all the D's of this thing will add up. Similarly for parallel capacitors, what will add here? Capacitance is epsilon naught A by B. So let me assume all the D's are same. And let the areas be A1, A2, A3. So A equivalent will be summation of areas. Okay, and this epsilon naught A by D, I can cancel on both the sides, will become C equivalent equal to summation of Ci. The factor of epsilon naught by D is constant for same for all the capacitors, so that will cancel. So from this I get this relation. Is that clear?
Yes.
So when I have parallel capacitor, assume that the D's are same. So the areas will get added up. So when I'm adding when capacitors are continuing parallel, so C equivalent is greater than mutual capacitance. C equivalent will be more than mutual capacitance, or it will be less. C equivalent and C1, which one is more?
In parallel connection.
Yeah.
C equivalent 1.
Because one way to understand this area is more.
Also.
This is true of any capacitance. So C equivalent is greater than any of the individual capacitance. And here, C equivalent is
lesser.
Because D is increasing. When D increases, the capacitance will decrease. So the equivalent capacitor will have more D. So the same E. So when you think connecting series, the capacitance will decrease. This is also again opposite to what's happening in resistance. And energy stored in the capacitor. So what is energy stored in the system? If you are doing work to build the system, then the energy gets stored in the system. Is that correct?
Sorry for what?
No. When will a system have energy? If you are spending some energy to build that system, or if you're doing some work to build that system.
On that system.
Yeah, on the system. Then the system will acquire some energy. Okay. Yes, so here we have to do some work to create this charge separation. Okay. So one way to create this charge separation is to take some electrons from here and transfer it here. I have to transfer the electrons from here to here. So the first transfer of electrons will happen without any work, but once I make this separation, because of this electrons here, there will be an electric field in this direction. So to move the second set of electrons, I have to do some work, because already the negative charge here will create repulsive force on this electron.
Yes,
So to create this final separation, I have to do some work. So that work is going into storing increasing the energy of the system, and that energy is half CV square.
yes, sir.
Okay. So you remember this formula, half CV square.
Yes, sir.
So one way to remember this formula is kinetic energy of the system is half mv square, right?
Yes, sir.
So this formula is similar to that. Instead of m, we have c, and here the v is velocity, here the v is voltage. So this one we have remembered the formula. This is an analogy. Okay, and once we get this formula, we can use Q equal to Cv to get other forms, these two.
Yes, sir.
Okay, so we can also associate an energy. Suppose there is electric field in this region. Okay, so the energy that is stored in this electric field, I can get it as half epsilon naught E square. Okay, this is energy in a unit volume. If I take this volume, see as a unit volume, the energy in this volume is E square. So we can say energy of the system is same as the energy in this electric field. This is electric field is there, no? So whatever is energy of the system is there in the energy of the field. So this is energy of unit volume, and this energy, if I multiply by the volume of the region in which the field is there, so this into the what is the volume of the region in which the field is there?
A into D.
So this into A into D will be the total, and this should turn out to be half CV square. Okay,
Yes, sir.
and that's not difficult to figure out, because if you put C equal to epsilon of A by D and V as E by D, you know why V is E by D? Sorry, V is E into D, right?
Yes.
Which is uniform electric field. So electric field into the distance will give me a potential difference. This you know, right?
Yes, sir.
Okay. Okay, let's just try to solve this problem. 2007. Two condensers, one of capacity C, another of capacity C by 2 are connected by a V volt. The work done in charging fully both the condensers are. Okay, so initially, say there is a switch here which is open. So initially, what will be the charge on these two? Zero.
Zero,
Right?
sir.
Yeah, zero. That is the starting condition. Others will become complicated. Okay, so once I close the switch, there will be a transient state. After that, it will be steady. And once it gets steady, there will be some charge here. Say Q1, and here the charge will be Q2. So you have to find work done to fully charge both the condensers. Try this one.
Third option, sir. Option 3.
3.
Yes, sir.
Yes. So there are different ways of doing this one. So one way is to find the equivalent capacitance across this one. So the equivalent capacitance C and C by 2 in parallel, the thing will add. So it's 3 by 2 C is the equivalent capacitance of this one. So 3 by 2 C, half CV square formula we use. So half 3 by 2 C into V square. So half 3 by 2 C is 3 by 4. So that's how you did?
Yes, sir.
Okay. So this one is series combination of the N1 capacitors, each of value C1 is charged by which is a series combination. Okay, have a potential difference of 4V. Okay, and another parallel combination Okay, into capacitors, each C2. Okay, source of potential difference is V. It has same total energy stored in it as the first combination. Okay, so you have to relate C2 and C1. Try this one.
The value of C2. Okay.
The thing is, total energy stored is the same. So that means C1 and C2 should be related in a certain way. So we have to find it. We have to find C2 in terms of C1. There's some background noise.
My door is open.
So if there are two capacitors in series, say C and C, what are the equivalent capacitance?
Sorry, what, sir? 3/2.
Okay. Yeah. So if there are three capacitors C, C, C in series, what are the equivalent capacitance?
2/3.
Yeah. So here there are N1 capacitors in series. So what are the equivalent capacitance?
C1/N1.
Yeah. So similarly, two capacitors in parallel. So N2 capacitors in parallel. So what are the, if there are say C, C, C in parallel, what are the total capacitance?
N2.
N into C, right?
Okay.
Yeah. So in the second case, the effective capacitance is N2 into C. So now we can solve the problem. This is 2010.
C1/N1 into N2, but
Which option? Option.
a numerical value to do.
Which option?
No, sir. I have to equate the energy only, sir.
Yeah, energy has to be equated because same total energy. So you have to equate the energy. That will give the relation between C2 and C1.
But the potential is same, no? So
No, potential is no. Why is he saying? He's saying no 4V. And the second case, the potential is V.
Okay.
Read the question properly. And as soon as you read the question, you have to write the content in the question in your paper. You have to read the question only once. That will save time. So as soon as you read the question, you just write it in.
Okay, these are often. Fourth option.
Just listen. So N1 in series, okay, and the potential is 4V, and N capacitors in parallel, the potential is V, okay. So and the energy is same, right? So half. So here the C equivalent would be C1/N. Here it will be N times C2. So half CV square. So C1/N into 4V square equal to NC2 V square. Oh, N1 and N2, right? Into V square will cancel. So C2 equal to N2 by N1 4 square 16. So option B, right?
Option D for N2 will come in denominator.
Okay, it's option D. So I made some mistake.
Yes, sir. N2 will come to denominator.
Okay, N1 and N2 both will be denominator. So option D is the correct one. So what I'm saying is, as soon as you read the question, you have to write on your paper. It's like this. Before solving the question, the full information of the question you have to translate in the diagram, like you have to write N1 and write a series picture, and the potential of potential is 4V, and this N2 are in parallel, and the potential is here is V. So convert, because you cannot underline on the computer screen, right? So yeah, this step you have to write first. Whatever is there in the question, you have to write in your own words. So after this, you have to start solving it. Otherwise you make silly mistakes. Another advantage of writing this thing is you have to read the question only once, or
Okay.
maybe twice if it's required, absolutely required. If you keep on reading question again and again, then it will take time, and also you make mistakes. So as soon as you read the question, whatever information is required, certain information you can store in your memory. But in addition to that, if you want to remember something, then you write it down like this. Okay, after that you start solving, because this step you don't skip, otherwise you'll make mistakes, and also you waste time reading the question again and again. Is that clear?
Yes, sir.
Okay. This one. Is this clear, the question?
Yes, sir.
See, there is a 10-volt battery, and there are some combination of capacitors. So obviously, under steady state, you don't charge these things, right? So some charge will get stored in these different capacitors. So if you know the charge that's getting stored here, or the potential difference across these two terminals, I can find the energy. Okay, he's asking to find charge only. Okay, either you have to find the charge, or if you find the potential, you can find the charge using Q equal to C into V. Okay, so you'll find the potential of these two across 4 volts, or you'll find the charge. You can find the potential, right, across this one.
How?
These two you can combine. So if you combine, what will you get?
6 microfarad.
6 microfarads. After that, 4 microfarad, 6 microfarad in series. So the charge across this thing will be, you can use the formula.
4 by 10.
Yeah. So
4 by 10.
it will be 4 by. So if the capacitance is more, the charge will be more. Is it a direct ratio or inverse ratio?
Direct ratio.
Actually, the charge is same, no? Because they are in series. So this is 6, no? So 6 and 4 I can combine. That will be 10. So 10 by 10 will be, so 1. What am I
So
doing?
no, the series 24 by 10.
Yeah. Series will be reciprocal. Okay, fine. So what is the answer?
2.4
Units?
microfarad.
No. Charge.
I have the equivalent capacitance value to 10.
You have to find the charge. So once you find the equivalent capacitance, that charge across the total equivalent capacitance is also same as a charge across individual capacitance. Because there is series, no? So what you got is correct.
Yes, sir. Yes, sir.
So 2.4 microfarad into 10, that will be 24 microcoulombs.
Yes, sir. 2.4 into 10.
So if you have two capacitors in series, Q is same. So the voltage, the charge will, okay, Q is same. So I can find the charge across the equivalent capacitance. That will be easier.
Yes, sir.
Okay, this one 4 capacitors. So you have to find the charge on C2 and C3, the ratio.
C1, C2, C3. The three are in series only, sir.
Yeah, these 3 will be in series. So the charge across C2 is same as the charge across this equivalent because they're in series, no?
Yes, sir.
So what is the charge across this equivalent and also the charge across this C4?
Mm. 22/3, sir. First option.
Okay. So C equivalent. So Q equivalent is 6C/11. And this C4 is 4C, right? 4C into B. So Q2 by Q4, Q2 is 6C/11. So 4, that is 3. Option B.
Option A, sir.
No. You made some silly mistake. It's Q2 by Q4.
C2 by. Okay. C2 is. C2 is 4 CV only, sir.
You want to make some silly mistakes. See, Q4 is C4 and V, right? Yes.
Sir.
That is 4C into V. And Q equivalent, you have to find Q equivalent is C equivalent to V. And 1 by C equivalent is 1 by C plus 1 by 2C plus 1 by 3C. And that C equivalent is 6C/11. So Q equivalent is 6C/11 into V. And Q equivalent is same as Q2 because everything is in series, no? So Q2 by Q4 is 6/11 divided by 4. So that is 3/22. Is it clear?
Yes, sir.
Okay, I'm going to make some silly mistake. Right.
2 times after 32.
Okay, this one, find equivalent capacitance between A and B. This is actually a trivial problem.
All are in parallel only.
Yeah, so to figure that out, the potential at B is same as the potential here. So these two are as if the same points, and same with these two are in the same point. So all these in parallel. So it will add, capacitors will add. Okay.
But How do you say that for B, B, A, that one can be explained?
How do you say what?
That A and A will have same potential, B and B will have.
Because this is connecting wire, no? Connecting wire means it's ideally zero resistance. So the current is zero, no? This is a conductor, no? Connecting wire is a perfect conductor. Connecting wire.
Why can't A and B will have same potential?
No, not A and B. This point potential is same as this point. So this point is same as point A only, as far as potential is concerned. This is connecting wire, no?
Okay.
Connecting wire is a perfect conductor. So in a perfect conductor, the electric field inside is zero, so there won't be any potential drop. It's a perfect conductor.
Okay. Okay.
Okay, so whatever is a potential at this point, the potential here is same as potential here, and same as potential here. Only across this element there will be a drop. Potential here is same as potential, 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 potential. Okay, so this point the potential is same as this point potential. So all the capacitors are between the points A and B. So it's as if they are parallel. Clear?
Yes, sir.
Okay. This one, find the equivalent capacitance between points A and B.
Between point A and B.
Here also you just have to see this point is same as this point. So this point potential is so same as A, and this point is also B. And here you have to introduce another term, so X. So there are 3 points. So A, X, B. So you have to redraw this circuit like this. So this capacitance between A and X, this capacitance between X and B, this capacitance between X and A. So these two capacitors will come in parallel because this and this are connected across X and A. And this capacitance between A and B. A and B, this capacitance. So this is the equivalent circuit.
So the conductor is not separately conductor.
Speak loudly.
I can't understand. So can you please draw it again?
See, this potential, see the point potential, this, what will you say, is the same potential here, right? Because these are connecting wires.
Okay.
So here also the potential is A, here also the potential is A up to this point. Okay, so here also the potential is A, here also the potential is A. So potential at point P and potential at point A are same. Okay, across it there will be some difference. So here the potential is B, here also B, here also B, here also B up to this point B, and this point let me call it as X. Okay, so the potential here is X, the potential here is X, the potential here is X. These are all connecting wires, no?
Yes, sir.
So basically there are 3 points, A, B, and X. So I'll read all this circuit A, B, and X here. So this capacitance, this one, is between A and X. That is this one. And this capacitance.
How to read the circuit again, sir?
No, just draw these points. There are 3 points, no, A, X, and B, as far as potentials are concerned.
You draw it on separate sheets, sir. Actually.
So basically there are 3 points here, A, B, and X. So I can draw anywhere, but just to have similarity with the already existing geometry or the locations, I'll draw A, X, and B like this. So this is point A, this is point X, and this is point B. So this is A, this is X, and this is B.
Okay.
So there are 4 capacitors, right? So this capacitance is between A and X, and this capacitance is also between A and X.
Yes, sir. Yes,
So
sir.
there are 2 capacitors between A and X.
They are in parallel. Okay.
Yeah. And all capacitance values are C. Okay, so these 2 capacitors are covered, and then this capacitance now that is between X and B, and this capacitance between A and B. So between X and B, there is one capacitance, and between A and B, so total 4 capacitors. So here also 4 capacitors. So now this is done. So now these two are in parallel. So it becomes 2C, and then 2C and C are in series. Okay, so it will become 2C is same as C is same as 2C by 2, so it will become 2C by 3, and then 2C by 3, and then C are in parallel, so it will become 2C by 3 plus C, so that will be 5C by 3.
Sorry, sir, what? This will become 2C, then
So this is 2C, no?
yes, sir.
And this C I can think as 2C series with 2C. Okay, this C I can write as 2C by 2, right?
Yes, sir.
And this is 2C, so these two, so this combination will become 2C by 3. If you have 3 capacitors, 2C, 2C, 2C in series, that will become 2C by 3, no?
Yes, sir.
C is same as 2C by 2, that is same as 2C in series with 2C. So this single C is equivalent to, that is the meaning of this, right?
Yes, sir.
So basically I have 3 2Cs, so that will become 2C by 3.
Okay.
Okay, in parallel with C, so it will be 2C by 3 plus C. So this is 5C by 3.
Yes, sir.
So correct option is option B. So equivalent capacitance between this also is exactly same logic. I'll just tell the method. So basically you have to figure out how many points with different potential. So this is A means this is also A, and B is this one. So there is only one B, because so if I call this point as X point with potential X, so this also same as X, and this also same as X. So basically there are 3 A, X, and B, right? So A, X, and B. Looking at this geometry, I'll draw A, X, and B like this only. So all the capacitors I have to draw like this, redraw like this. So this is the equivalent circuit. So this is trivial. 3C in parallel
Sir,
with.
sir, last addition of service is
Talk loudly.
Can we do this again in separate sheet?
No. You can do it. See, this figure is clear, no?
Yes, sir.
So you have to draw. See, there are how many points? A, X, and B, right? 3 points.
Okay.
So since this A, X, and B is like a straight line in this original figure, I'll draw in the same pattern here also.
So totally 3 parallel capacitors.
No, the 3 points A, X, and B are in a straight line like this, no? In the first one, horizontal. So the same way I draw
Yes, sir.
A, X, and B. So this capacitor 1 is between A and X. So this is 1, and 2 is between X and A. So this is 2, and 3 is between A and X. So that is the third one. And fourth is between X and
Y.
Okay, having introduced one more point here. No, these two I can combine. These two, 4 and 5, I can combine as C by 2, right? So C by 2 is between X and X. So C by 2 between X and X, it will drop out. It's like a short circuit. So I can forget 4 and 5. 4 and 5 is
If they are connected to same potential means we can leave them, sir.
Yeah, that's what 4 and 5 are out. So this is 1, 2, 3. 4 and 5 are not required because they are connected in 2 points of same potential. So it's as if
Okay.
those two are not there. And 6 is between X and B. So this is 6.
Yes, sir.
So this is a very simple
Yes, sir.
circuit. Done. Okay.
DC. Yes, sir. DC by 4.
This is also very simple. Okay, this is a different concept. Right. So this one, how will you solve? How to find equivalent capacitance? What?
These similar
Yeah.
kind of problems solved before, sir.
Yeah. So this is Wheatstone bridge.
But yes, sir. 1/2, 1/2. Sorry.
No, you have to speak loudly.
Yes, sir.
Okay. So this is a Wheatstone bridge and it's a balanced Wheatstone bridge because 1/3 is same as 2/6.
Yes, sir.
Okay. So since that means the potential at this point,
Same.
potential at this point and at this point are same. So you have an element connecting the 2 points with same potential as if this thing is not there. So you can remove this thing. Once you remove this thing, these two are in series, these two are in series, and then these two are in parallel. So it's a simple circuit. So you'll get the answer here. Okay. So Wheatstone bridge, right? You already know. Fine. This one 1999. So find the effective capacitance between X and Y. So X is here, Y is here. So try this problem.
None of them are in parallel connection.
Is there a Wheatstone bridge here? Can you see a Wheatstone bridge in this problem?
No. I didn't find it.
So this is a Wheatstone bridge. So you have to find where the Wheatstone bridge
C1 and C3 and C2 and C4 are in. They have same potential, no, sir.
These
The
two points are
ratio.
in the same potential.
Ah,
So you can remove this element. Okay. Once you remove this element, these two will become in series. And similarly, these two will come in series. So I can combine these two and these two, and these two will become in parallel. So what is the answer?
24 microfarad.
6 and 6 in the series is how much?
Not series. Series, sir.
See, I will remove this thing. No, once I remove this thing, these two will become in series. No.
Okay, 3 microfarad.
Yeah, and this one is also 6 and 6 in series. No.
3 microfarad.
So what is the combination?
6 microfarad.
So option
D.
D is the correct one. See, one way to check whether a Wheatstone bridge is there or not. I'll give an analogy situation. See, suppose this is a water tank. So there is water inside, and have two pipes like this. Okay, which are bringing the water down. Okay, now if I connect this two pipes with the third pipe, like this, will the water flow in this pipe? And suppose if I connect this thing by pipe like this, will the water flow in this pipe? And say another third pipe like this, will the water flow in this pipe? Water in this pipe, the water will flow in this direction, right? In this pipe, the water will flow in this direction. Here, there won't be any water flowing because they are connecting the 2 points which are at the same level. Okay. So similarly, here also in this Wheatstone bridge, there are two paths. So the charge can flow along this path. Okay, and this is the second path, and this is this sort of connecting pipe like this, the blue one. So the charge will flow in this connecting pipe if there is a potential difference between these 2 points. So here there is no potential difference here and here, so there will be any charge flowing. But if I connect like this, then there is a potential difference in the flow of charge will be there. So one way to look at which one is just see that there are two paths from initial point to the final point. So these are the 2 points, and there is a connecting branch which is touching these two paths. So whether this thing will charge will flow in this branch, that you have to figure out. This one, infinite ladder, you know, right?
No, sir.
You have not done problems like this.
Never, sir.
Okay, so this is see here the capacitor connected is 2 microfarad, 1 microfarad, 2 microfarad, and it goes on to infinity. That's important. Okay, so if I look at this circuit, say across the this point, say, okay, if I look at this across this point, okay, will it be same even if I look at this circuit from this point? Will it be same? Because here it's infinity, it goes on to infinity. So the effective capacitance across this blue line is same as the effective capacitance across this purple line, because it's infinite, no? Is that clear? Okay, so if I call the capacitance across this point as C, then the whole thing I can replace by C. So this circuit I can redraw as across A and B. So this is A, this is B. So 1 and then 2. So this is 2 microfarad. This is 1 microfarad. And these 2 points I have. So whatever is, let's see here, the equivalent capacitance C. And the capacitance across CAB will be equal to 2 microfarads, and C, let this also be C microfarads. So this 2 and this C are in parallel, no? So the combination will be 2C divided by 2 plus C, and that is in parallel with 1 microfarad. So this is 1, and CAB is same as C. Because the capacitance are seen from this purple line is same as the capacitance seen across this blue line. Capacity of this blue line is C. So that is same as this one. So 2 and C are in series. So the effective is 2 C. And this is parallel with that. So can you solve this one? You'll get the answer. So
I can't understand the point. What is CAB equal to?
See, this is the capacitor across this blue line, right? As seen from this one. And the value of capacitance seen from this thing should also be C. The capacitance seen from this blue line is C. The capacitance seen from this one is also C.
Okay.
Because it's infinite, no? So,
Yes.
so this is C means I can put a capacitance of value C here. So 2 and C are in series. So the combination is 2C by 2 plus C.
No, sir.
Then,
Parallel means they get added, not 2C only. No.
okay, okay.
2 plus 3.
Yeah, I made a mistake. Okay, okay. Did you solve it? Get the answer? No, this thing is in series, no? 2 and C are in series. So it will be combination is what it is correct.
Okay. You said that was parallel.
2 and C are in series. So it is 2C plus 2 plus C. And this is parallel with 1. So that is one. That is the capacitance across CAB. That is same as C. Okay, so this you have to solve for C. So that is just solve this one. You'll get the answer. Oh, sorry. It's C microfarad. That's equal to C.
That C value, sir.
No, C value is not. C is the one we have to find out. There is only one variable. C you have to find out.
How can I find it?
So this is C squared minus okay, so this is minus 2 and split into factors should give me minus 1. So minus 2 plus 1. So this is C minus 2 C plus 1.
C equal to 2 also.
So C equal to 2 comma minus 1. So this 2.
Capacitance be negative, sir.
C cannot be negative, so we have to neglect that.
Okay.
So C equal to 2 is the answer. We got it now on 2 microfarad because the effective capacitance is taken as C microfarads. Is this clear?
Yes, sir.
So you have to find what is repeating. So whatever is seen from the blue line is same as whatever is seen from the purple line. So if we assume the capacitance seen from the blue line is C, then the capacitance seen from the purple line will also be C. And C in this 2 and are in series, which is parallel with 1. So that combination should be equal to C. Okay, this one. So this one problem, have you seen already or not? There are 4 metallic plates, okay, and the top plate C and the bottom plate D are connected by a conducting wire, and A and C are connected to the battery. So have you seen problems like this?
No, sir.
Okay. Right. So the playlist, did you try to see the problems in that one? Electric field and charges. chapter 1. I sent you the playlist, right?
Yes, sir.
Did you
Tonight one, that one.
yeah, did you see problems in that?
No. Tonight one I will do this problem.
No, yesterday I sent. Okay, you have to practice problems. Either see, the thing of advantage of giving that playlist is solution is there. So if you cannot
Yes.
if you cannot get the solution, you can look at the solution. And another thing is this another link I sent, ESRL. Okay, so that also you can use. So you have to practice problems. Otherwise, so here go to electrostatics or capacitor separately is there. Electrostatics is and capacitor is there. So this will be chapter 1. This will be chapter 2. So click on this capacitor. You will get previous questions. Okay, this is the same question we solved. This is a which one bridge, right? There are two parts, 1 and then 2. And connecting these two parts is this in between this one. So potential points B and C are same. This thing can be neglected. Okay, and the values, everything is given as 4. So obviously, so capacitance C2 is 10 microfarad and the effective capacitance. So C2 is a different value. All the other capacities are same. So it's a balance which
4
one.
microfarad.
Yeah, so this thing will go away. Right. So you can try problems in this one also, in this ESRL also. So you have to practice problems. So you will do that today.
Yes, sir.
Okay, already have. So either you do this one or you can do the playlist also. But this is more relevant for you because this is aims and NEET. Okay.
Yes, sir.
So do this one and do that one. Which one you feel like doing? Okay. So tomorrow, should I move to the next chapter, current electricity?
No, but okay, we'll see, sir. But we didn't solve more problems regarding the dipole and then sir, the potential energy later problem.
Dipole, the potential due to dipole is along the axis and perpendicular in the equatorial plane, right?
Potential energy related problems and
Potential energy is P dot E minus P dot E. Potential energy of a dipole in external
related
electric.
problems are more in sir.
Yeah. So yeah, you should try problems, and if you're not getting the problems, you just send me a snap.
Okay, sir.
Just a minute. Here, electrostatics. Okay, electric balance charges Q and its diagonal speed is based on uniform electric field. Okay, so these sort of problems you should be able to solve. So just click this electrostatics. You get problems here. So try these problems. If you're not getting it, you let me know. These things you should be able to solve. Electric dipole has a magnitude of charge Q, dipole moment P, find it is placed in uniform electric field. Okay, dipole moment is along the direction of the field. So you have to draw the picture immediately. Force on it and potential energy are respectively. potential energy is minus P dot E. So P dot E are respectively, okay, the other options are minimum or maximum to find out. Potential is actually minus P dot E. Okay, minus sign is missing here. So it's along the direction of the field. So along the direction is minus P dot E. So angle bit, so it's cos 0. So it will be minimum. So potential will be minimum. So these two options are, it should be within these two. This is wrong. This is also wrong. And force on it is, force is always 0 because it's uniform electric. So correct option is option 2. Is this clear? 6 is option 2. God. Six is option 2, yeah.
Yes, sir.
So okay, maybe tomorrow I'll solve some few problems on dipole, but you already solved problems. Everything is there for you. I've given you this link, right?
Yes, sir.
So try these problems. So whichever problem you are not getting, you just let me know. And then tomorrow, if you want, I can do these problems. And, after that, I'll start this current electricity.
Yes, sir.
Okay, fine. Okay, meet tomorrow.
Bye.
Okay, bye.